Welcome to the Hughes Communications Lab of the University of Maryland at College Park. I'm Alejandra Mercado. I'm Associate Director for the Masters in Telecommunications program at the University of Maryland at College Park. I'm also an instructor, a mentor, an administrator, and a lab coach. The Hughes Lab provides hands-on experience where students learn to work with the ETIS B210 software-defined radio, as well as the Gnu Radio Companion, which is a front end to the Gnu Radio libraries for digital communications and signal processing.
And this is a really important thing for you to be able to know, is the purpose of raised cosine, okay? So first of all, you and I know that the Fourier transform of a rectangle is a sinc function, right? And a sinc function goes on forever, which means that you and I cannot transmit rectangles over the airwaves, because if I do, then I occupy an infinite spectrum and the FCC will come and they will, put me in jail and fine me and take away my license. Now, you might argue, can I filter this wave before transmission? And if you do that, in order for the FCC not to give you any problems, then these sharp rectangles will actually become, good morning, these sharp rectangles will actually become smoother, right? They won't be as sharp. But then the question, comes to mind, like, is this the optimum choice, to create a rectangle and then to filter that rectangle? Now, we want something smoother, something that occupies less bandwidth, right? The problem with smoother is that you get spillover in time. One symbol causes interference to the next symbol. So for example, this +1 bit interferes with this -1, the 0 bit, okay? This is called intersymbol interference. In this case, we're talking about bits, but in general, it could be, any particular symbol would work just fine. And you would have the same problem, okay? So the question is, I want to have a smoother symbol. I want to occupy less spectrum, but I want to avoid intersymbol interference. I want the newer symbols not to interfere with the older symbols, and vice versa. So we want a smooth shape that also does not interfere with past symbols. And the solution is that the shape that satisfies this criteria is the raised cosine filter, okay? What does the filter look like? In the time domain, the impulse response of this filter looks like this, okay? It crosses 0 exactly at multiples of the sampling interval. TS, 2TS, 3TS, 4TS, da, 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 da. Now, if we look at the same filter in the frequency domain, it's going to have this shape where it goes to 0 at 1 over the bit duration. It should actually be the same TS, but never mind. And it is symmetric across 0. It crosses the midpoint 1 over 2 TB or TS. And these pictures, I made them in MATLAB, but they're not as pretty. As a matter of fact, Wikipedia made prettier pictures. So because we're allowed to use Wikipedia things, images, I'm reproducing them here. In the time domain, you can see that exactly at the symbol interval, this impulse response crosses 0. And in the frequency domain, it goes to 0 at 1 over t, and the minimum point where it goes to 0, when the roll-off is equal to 0, beta is equal to 0, it's 1 over 2t. And the raised cosine filter can have several shapes depending on the parameter beta. And in Wikipedia, they did, in my example, I did beta equal to 0.25. In Wikipedia, they offer the blue one is beta is 0, the green one is beta is 0.25, the red one is 0.5, and the cyan one is 1. As you can see, when the roll-off is 0, you get a perfect filter, a perfect rectangular, sort of idealized filter. We call that the Nyquist filter, where it is perfectly flat with gain 1 in the passband, and then it drops instantly at 1 over 2t to gain 0. As the roll-off gets bigger, as you can see, it smooths out until it reaches the maximum roll-off, where you just get a pure, smooth waveform in the frequency domain. For all of the beta, if you'll notice, the crossings are at 0. Can you see that? All the crossings are, excuse me, not at 0. The crossings are at the symbol interval, right there. All of them are 0. And you might wonder, why do I keep repeating that and emphasizing it? Well, what is the point? What is the advantage? What's so special about the raised cosine filter? The answer to that is it minimizes intersymbol interference. Let's put several symbols, one after the other, at one symbol distance from each other. So here's one symbol centered at 0, and the next symbol is centered at 1 symbol interval. And look at what happens. Exactly at the point where this peak is maximum, this other peak drops to 0. Indeed, for every symbol, you're going to find that where the peak is maximum, all the other symbols are exactly crossing 0. And that's the very special property of the raised cosine filter. All right? So if you ask, if I ever ask you on, a quiz or something, what's so special about the raised cosine, you're going to say, first of all, it has less spectral regrowth. It has less spectral occupancy than a rectangle function, just a plain, unfiltered signaling. And it has the wonderful property that it mitigates intersymbol interference. Okay? So here's one problem that we run into at this point. We know that the transmitter needs to filter its signal before transmission. We want to avoid problems with the FCC. We want to avoid problems of imposing interference on other systems and on adjacent carriers. But we also know that at the receiver, we want a filter as well. And we talked about this before. Any signal that is outside the desired bandwidth, whether it is an adjacent user or whether it is out of band noise, all of those signals, we want to eliminate them at the receiver. If you don't eliminate them, you run into the danger that somewhere down the line at the receiver, you're going to have some device that behaves non-linearly with respect to some adjacent channel user. And when that happens, you're going to have harmonics, you're going to have, remember we talked about this in lab number 3 and in lecture number 2, the nonlinearity is going to cause spectral regrowth. And that spectral regrowth may actually come back and cause interference in the desired signal inside of our band. So in order to prevent that from happening, the first thing that happens with a signal in the receiver is you filter it. So now we know that there's a filter at the transmitter and the filter at the receiver. What we would like is that the combined effect of both filters from the transmitter and the receiver, together, they act like a raised cosine. So since both the transmitter and the receiver collectively are each going to have a filter, and collectively we want that to be the raised cosine, at each transmitter and receiver we use the root raised cosine. The root raised cosine, so this is the transmitter, our signal, our QPSK signal is going to go into the root raised cosine filter. The output is the convolution of the impulse response of the root raised cosine with our QPSK signal. Then it goes into the channel. And I kind of ran out of space here, so I drew it a little bit to the side. At the receiver, the signal that has already been filtered by this root raised cosine is fed in the receiver to another root raised cosine. So at the receiver, the output of the filter is going to be QPSK signal convolved with the impulse response of a root raised cosine and another impulse response of the same root raised cosine. Obviously here I'm not talking about the additive white Gaussian noise. I'm not talking about channel distortion. I'm not talking about anything yet, because in today's lab we're going to forget about the channel for the moment. We're going to address that later. So for today's lab, assume that there's no channel. We just want to see what happens with the root raised cosine. So in the time domain, you have a QPSK signal with convolution out of each of the filters. But when we look at it in the frequency domain, we know that convolution turns into multiplication. So the output of the transmitter's root raised cosine is the transfer function times the other transfer function. And then at the receiver, the product of this times the receiver transfer function, which means we get this squared. Right? This times this, we get it squared. We designed the RRC filter, root raised cosine filter, so that when you square it, it actually yields the raised cosine filter. In other words, that's why we call it root, as in square root. Okay, you multiply these two together, you get the raised cosine. Okay, so in today's lab, we're going to see one root raised cosine in series with another. The transmitter is going to have the root raised cosine, and then the receiver has its own root raised cosine. Note, I want you to remember one of them is not enough. One root raised cosine filter alone does not mitigate the ISI. You need both, and we're going to see that today. You need both the RRC in serial, one after the other, to get the RRC squared, which is the RC, which enjoys no ISI. So again, this is in the absence of a channel and multipath fading and all of this. So in today's lab, you're going to see the QPSK constellation with intersymbol interference, because it only has one RRC, and then without it when you have both RRC. Now, the GNU Radio Companion constellation modulator block actually uses a root raised cosine to generate its digital symbols. In our case, it's going to be a QPSK constellation. So the GRC uses root raised cosine to generate its digital symbols. And therefore, we're going to have to apply one more RRC. Okay. In our case, we're asking, this is one of the parameters that you enter into the constellation modulator. In our lab, we're asking the GRC to use 4 samples to represent each symbol. In other words, as far as the GRC is concerned, each symbol is going to be represented by 4 samples. And you can vary this, but in our lab, it'll be 4. So each symbol represents by 4 samples, and since our sampling rate is going to be 10,000 samples per second, that means that every symbol will take, 4 samples per symbol, 10 divided by 10,000 samples per second, you get 1/2500 seconds per sample. That's the duration of one symbol. All right. So we are asking, therefore, the following root raised cosine filter to decimate by 4. Remember, we talked about decimation. That's when you throw away 3 out of the 4 samples. So we're going to end up with 1 sample per symbol instead of 4 samples per symbol. So we know that the symbol rate 1/2500 seconds per symbol is 1 over that is 2,500 symbols per second, which is what we're going to enter into the root raised cosine filter parameter. After decimation, we are asking GRC to throw away 3 of the samples and keep 1 of the samples. And you might well ask, how does GRC know to choose the best sample? Why doesn't it choose one of these? And that's a very good question. As a matter of fact, the GRC block has a mechanism to choose the optimum sample. But later on in a later lab, we're going to see what happens when you choose a different sample, not the optimum sample. But that's not going to happen today. Today, we're just going to leave the GRC block to its devices to choose the optimum sample. So each symbol now will be represented by 1 sample. And this is what today's lab, GRC lab, is going to look like. I'd like you to rename it QPSK with pulse shaping. The sampling rate is 10,000 hertz. Then I would like you to form a random source between 0 and 256, which means that the random source is going to generate 8 bits at a time, and the bits can take on any values between 0, 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1, which is 255. And randomly, it will produce a bit sequence between any one of these values. And then it's going to just keep generating this. Then we have the constellation modulator. The constellation modulator is going to use the QPSK. It is going to map, let me get this out of the way a little bit. It's going to map each one of these values to these constellation points. So for example, 0 is going to be mapped to -1 minus j, 1 is going to be mapped to -1 plus j, 3 is going to be mapped to 1 plus j, and 2 is going to be mapped to 1 minus j. And we're giving the instructions to the constellation object to set up these constellation points. And again, we said here that the constellation modulator was going to use 4 samples per symbol with a root raised cosine filter. At this point, we're going to see what happens when you differentiate. In one case, we're going to apply another root raised cosine filter. Therefore, the output of this should be raised cosine filter. At this point here, we have a pure raised cosine filter. Decimation by 4 means that the GRC is going to throw away, out of the 4 samples, it's going to throw away 3 and just keep 1, the optimum one. This one is going to decimate by 4. And it's just going to be an identity filter. In other words, it's just sort of like multiplying the input by 1. It doesn't do anything else except decimate. And then in each case, we're going to look at the constellation sync.
We'll first plug in the graph without the second root raised cosine filter and unplug the graph that comes after the second root raised cosine filter. Then we must compile to create the Python script, the Python code, and run it. We see that the error in sampling causes intersymbol interference, just as we expected. Next, we'll plug in the graph with the second root raised cosine filter and unplug the other one. Again, we have to create the Python code and then run it. We see that after the output of the filter stabilizes and converges, there is no error in sampling. The 4 constellation points are perfectly placed. Our lab confirms what we expected to see. The raised cosine filter eliminates intersymbol interference. So here are some of the questions that we're going to address in today's discussion. What are the roll-off values that we can select for a raised cosine filter? And how does the selection of roll-off affect the filter response? What are the main requirements of any pulse shaping filter? And how does today's lab achieve that? What limitations are placed on the signal's bandwidth? And why do we decimate the discrete time signal? Here at the Masters in Telecommunications program, we strongly believe that the best student experience involves hands-on labs and projects to equip our graduates to excel in the workplace. One of the things that attracts students to our program is that we are very industry focused. We keep a constant tab on the skills that hiring agents want, and we make sure that we offer courses and labs that provide these skills.